In the last set of lectures, we talked about torsional loading of shafts and included circular shafts, box shafts, and open box sections. So I want to talk a little bit about that using my Fusion 360 results to show you exactly what's going on. I have in this particular FEA analysis a 50 by 30 millimeter rectangular cross section that is subjected to a torque that's trying to twist it around the y-axis, which goes right up through the center of this particular box beam. And you will notice a couple of things about this box beam. So let's go ahead and look at the top of it. You can see that it twists. You can see that it twists, in fact, counterclockwise. I've exaggerated that twist so you could see it. You can see that the maximum shear stress is at the center of the long section, just as was shown by the equations that we presented for the quick analysis. And the stresses at the corners are going to be zero. You can see 90-degree angle of the corners is retained. There's no deformation at the corners in this. Now let's go ahead and take a look at a box beam, an open box beam, a thin-walled instead of a filled section. And if you look at a thin-walled section, same dimensions, 50 by 30 centimeters, 1 centimeter wall thickness, and you'll see a lot of deformation as we subject this to a torsional stress around the y-axis. So if we look down on it, we're rotating counterclockwise as you're looking at this. You'll notice a couple of things. First, that there's a lot of deformation in this open beam. Second, that the 90-degree corners are retained where the shear stress has got to go to zero. And so we get a lot of deformation in an open beam. So both the square sections, the rectangular sections, and the open sections are not efficient at carrying torsional loads. As we move forward in this lecture, we're going to be talking about thick and thin-walled pressure vessels. So I just did some CADing up of some thick-walled. This is an example of a thick-walled pipe that is internally pressurized, and that internal pressure goes from a maximum on the inside to a minimum on the outside, and we will compare these results to what we do through hand calculations. This is a thick-walled, meaning the wall thickness is greater than 1/10 of the radius. If we look at a thin-walled cylinder, we get a very different kind of picture. Top view of this one shows the thin-walled section, and in the thin-walled section, we end up with a hoop stress, which is essentially uniform through the thickness. So we will compare our hand calculated values to the FEA generated values so you can see how the simple equations compare to a numerical analysis.